Chapter 1. The Golden Mirror. Roan Point 5 million kilometers from Earth. Lagrange Point L2. Here, in absolute darkness and vacuum silence, at temperatures of -233 degrees Celsius, golden honeycomb panels slowly unfold. 18 beryllium segments, coated with the thinnest layer of gold, assemble into a single mirror. This isn't just an engineering marvel. This is the most expensive scientific instrument in human history. The James Webb Space Telescope begins its hunt for ghosts from the past. But here, in the vacuum, there is no room for emotions. Only cold calculations of trajectory and thermal shield checks. At the same time, in Baltimore, at the Mission Control Center, the silence feels different. It is electrified. $10 billion and 30 years of work by thousands of engineers now depends on a stream of zeros and ones traveling through the cosmic void. For the shift operator, this moment lacks romance. His eyes dart across telemetry lines. Cryocooler pressure, nominal. Detector voltage, normal. All systems operating as designed. He waits for the first image, but professional instinct whispers that the anticipation of triumph often borders on catastrophe. Webb's main advantage over its predecessor, the Hubble telescope, lies in its ability to see the invisible. It works in the infrared range. This allows an astronomer's gaze to pass through dense dust clouds that hide star birth and peer into an epoch when the universe was still very young. Light emitted by the first galaxies has traveled to us for more than 13 billion years. During this time, the expansion of space stretched its waves, transforming visible light into infrared radiation. And it is precisely this ancient, tired light that the golden mirror now catches. The first deep field appears on screens. Galaxy cluster SMACS 0723. To a casual observer, this looks like a scattering of precious stones on black velvet. But the operator sees something else. He sees a patch of sky the size of a grain of sand held at arm's length. And in this tiny grain, thousands of galaxies shine. The gravity of the massive cluster in the center works like a lens, bending and amplifying light from objects far behind it. This gravitational lensing allows us to see what lies beyond the capabilities of any optics. However, the excitement of the first seconds quickly gives way to cold bewilderment. The operator zooms in. He looks at spectral data from the most distant, barely visible red dots. According to all textbooks of cosmology, according to the standard model we've built over half a century, here at the dawn of time, we should see chaos, shapeless gas clouds. The first timid stellar clusters just beginning to gather into protogalaxies. This should be the universe's infancy. Chaotic, dark, and uncertain. But the data on the monitor shows a completely different picture. Instead of formless clouds, we see clear, structured spirals. Instead of the dim glow of primordial hydrogen, instruments register bright light, saturated with oxygen and carbon. These elements are born only in the cores of dying stars. To fill a galaxy with them requires generations of stellar cycles, hundreds of millions of years of evolution. But these objects simply didn't have that time. They look too mature for their age. This is like taking a childhood photo of your grandfather from the maternity ward and seeing not an infant, but a gray-haired old man with a lifetime of experience. It is a logical paradox. In astrophysics, time equals distance. The farther we look, the deeper into the past we dive. And we're looking at a past only 300 minus 400 million years after the Big Bang. There cannot be such giants there. This is forbidden by the laws of physics we considered immutable. The operator checks calibration. Perhaps it is a sensor error, a data processing glitch. But the self-diagnostic system glows green. Mirrors are aligned to nanometer precision. The near-spec spectrograph works flawlessly. These galaxies are real, massive, calm, and they exist where they shouldn't be. The image that should have confirmed our theory of world origins suddenly turned into evidence against it. We expected to see the beginning of history, but saw its middle instead. In the scientific community, this phenomenon has already been dubbed the eerily massive galaxy problem. But behind this dry term hides the existential horror of a theorist. If these galaxies exist, then our understanding of the universe's timescale is wrong. Either matter in the early universe behaved completely differently, violating the limits of gravitational compression, or the universe itself is much older than 13.8 billion years. Any of these options means the foundation of modern physics has cracked. We've encountered a crisis that cannot be ignored. This isn't just a spot on a photograph. This is a challenge to the ΛCDM model that describes our world structure from the Big Bang to the present day. If we can't explain these galaxies' origin, then we don't understand how gravity works, or we don't understand how time flows. The James Webb Telescope, created to provide answers, has asked us a question that could bring down the entire scientific picture of the world built since Einstein's time. Now we face a difficult investigation. We must examine every brick in our universe's foundation, from dark matter's nature to the constancy of light speed. I'll take you through the chain of discoveries and paradoxes that this single image revealed, and at the end of our journey, we'll have to answer the main question now hanging in the silence of mission control. Did the universe really begin with the Big Bang? Or are we simply not seeing the true beginning? Chapter 2: The Impossible Galaxy. In Moscow, at the Institute for Space Research, it is quiet now. Gray autumn light falls on a desk where a printout of spectral analysis lies. To an outside observer, this is just a broken line resembling a cardiogram. But for the astrophysicist who has been staring at this graph for 3 hours, this line means the cardiac arrest of modern cosmology. We've moved from the panic of first moments to cold, methodical horror of recognizing facts. The data obtained by the telescope doesn't disappear when you wipe your glasses. It lies before us, and it demands explanation. To understand the catastrophe's scale, we need to look at the specific culprit of this uproar. In 2024, the JADES collaboration discovered an object that received the code name JGDSS 14-0. Behind this dry set of letters and numbers hides a galaxy whose very existence breaks all game rules. We look at it, and our instruments record a redshift, denoted by the letter Z, equal to 14.32. In the world of astrophysics, this number is a death sentence. It translates into the language of time quite unambiguously. This redshift value tells us we're seeing light emitted just 290 million years after the Big Bang. By universe standards, whose age is 13.8 billion years, this isn't even infancy, it is the first moments after birth. At this time, space should be dark, filled only with rarefied hydrogen and the first still, timid clumps of matter. There simply shouldn't be anything complex there. But the graph on the Moscow office desk screams the opposite. Instead of a rarefied gas cloud, we see a full-fledged bright galaxy. Its mass is estimated at hundreds of millions of solar masses. Try to grasp this paradox. The universe simply didn't have time to gather so much matter. According to the standard ΛCDM model, gravity works slowly. It should have assembled this constructor atom by atom, grain by grain, over billions of years. But before us is an object that looks as if it skipped all evolutionary stages and was born already adult. But mass is only half the problem. The spectral analysis our astrophysicist is looking at reveals oxygen presence. And this circumstance frightens scientists even more than the galaxy's size. Oxygen isn't born from emptiness. It is a product of thermonuclear synthesis in massive stars' cores. To fill a galaxy with oxygen, entire generations of stars had to be born, live their lives, burn their fuel, and explode as supernovae, scattering heavy elements through space. We fall into a closed circle of logical contradiction. To get so much oxygen in 290 million years, star formation processes would have to proceed at incredible, physically impossible speed. This is like planting an oak seed and seeing a century-old tree with a mighty crown standing before you a minute later. Biology prohibits such growth acceleration. Physics, we thought, does too. But the James Webb Telescope impassively records the tree exists. In the Russian scientific school, it is customary to trust theory. We're used to equations describing universe evolution being reliable as rock. But object JGDSS 14-0 turns these equations to ash. Astronomers have already given such objects the unofficial nickname universe breakers. If you try to fit this galaxy into existing computer models, the simulation will error out. The program will tell you that creating such a structure requires at least 1 billion years, and you have only 300 million in reserve. Here comes into play a rigid physical limitation known as the Eddington limit. This is the maximum rate at which a star or black hole can absorb matter without tearing itself apart with its own radiation. Matter cannot fall onto a gravitational center faster than a certain limit. Light pressure will simply throw it back. To gain the observed mass in such a short time, this galaxy would have had to feed on matter while violating the Eddington limit, which contradicts fundamental thermodynamics laws. The astrophysicist sets aside the printout. Outside the window, Moscow's garden ring bustles. The world lives its life, unaware that its history has just been rewritten. The problem isn't that we found something unusual. The problem is that such galaxies' existence makes our standard cosmological model invalid. We built science's edifice on a foundation, assuming a certain rate of gravitational compression. And now it turns out that either gravity in the early universe worked differently, or something's wrong with the timescale. Imagine using a clock that sometimes runs fast, sometimes slow, by a century. If we see mature galaxies where they shouldn't be, perhaps the universe itself is significantly older than the accepted 13.8 billion years. This thought seems heretical. It contradicts Planck's satellite data and cosmic microwave background measurements. But Webb's data cannot be ignored. These aren't theoretical constructs. These are direct observations. Skeptics might object. Perhaps this is an interpretation error. Maybe the galaxy appears massive due to dust or special star arrangement. But Webb's infrared eye sees through dust. It sees the object's thermal structure, and the more we analyze data, the clearer the picture becomes. These galaxies are incredibly dense and compact. Such a galaxy's radius might be dozens of times smaller than the Milky Way's, but stellar density within it goes off the charts. It is a stellar metropolis, arising in the middle of a desert. We've encountered a phenomenon requiring new physics. The standard ΛCDM model, including dark energy and cold dark matter, brilliantly explained space structure on large scales. It predicted galaxy distribution, background radiation temperature, but it broke down at time's dawn. It cannot explain how chaos turned into order so quickly. This is cosmology's crisis, and it is happening right before our eyes. Every new deep space image coming from Lagrange point L2 drives another nail into old theory's coffin. We hope to see the first stars, so-called population the third, giants made of pure hydrogen and helium, devoid of metals. Instead, we see galaxies enriched with carbon and oxygen. We see traces of life and death that occurred before life and death became possible in the universe. By our calculations, this paradox forces scientists at ICI, CERN, and Princeton to seek answers in theoretical physics' most exotic corners. If matter couldn't assemble so quickly under ordinary gravity's action, then there was a catalyst, something that accelerated the process 1,000-fold, what could have served as the seed for these gigantic cosmic structures. The answer may lie in objects that themselves violate familiar logic, in black holes, but not ordinary black holes born after stellar death, but primordial ones that could arise within seconds after the Big Bang, when space itself boiled with energy. If this hypothesis is correct, our picture of creation will flip upside down. But while the astrophysicist in his office sees only an impossible graph, the equations don't add up. And in this silence, understanding is born. We don't just not know something. We know something that is wrong at the very foundation. The James Webb Telescope works perfectly. It doesn't lie. Our understanding of time lies. Our confidence that we understand how this universe began lies. We searched for childhood photos of space and found a portrait of a mature person. And now we must figure out who switched the album, or, which is much more frightening, perhaps there was never any birth as we imagined it at all. Chapter 3. Searching for Errors. The first reaction of any competent specialist to a discovery that breaks physics isn't delight, but cold skepticism. When data about giant galaxies in the newborn universe appeared on mission control screens in Baltimore, nobody ran to open champagne. Instead, tense, almost ringing silence settled in the hall, broken only by server rack humming. Operators and engineers responsible for James Webb began doing what they'd been taught for years, looking for errors in their own eyes. For an observer inside this sterile space, what is happening resembles investigating an air crash that hasn't happened yet. But indicators are already screaming about inevitability. The mission operator looks at raw data not as a window into eternity, but as a set of potential failures. Broken matrix, infrared sensor calibration error, software bug in frame stitching. Psychology of science is such, it is easier to believe a $10 billion instrument broke than admit reality itself broke. The main suspect was photometry. This method of determining galaxy distances works on color assessment principle. The redder an object, the farther it is, since universe expansion stretches light waves. But space has lots of dust that can also redden a star. If we mistook a nearby dusty galaxy for a distant giant, then the whole sensation is just an optical illusion. To exclude this probability, Webb was commanded to conduct spectroscopic analysis, the most precise procedure in the astrophysicist's arsenal. Spectroscopy isn't just photography, it is taking fingerprints from light. The NIRSPEC instrument, the near-infrared spectrograph, decomposed object, JGDSS, 14-0's radiation into components to find chemical element absorption lines. These lines work like a barcode. If the object is truly at the universe's edge, the entire barcode should be shifted to the red region by a strictly defined amount. Waiting for these graphs was the longest in the team's life. The result that came from Lagrange point L2 left no room for hope of error. The spectrograph confirmed redshift with frightening precision. This isn't dust or detector failure. We really are looking at an object whose light traveled to us for more than 13 billion years. But distance confirmation only worsened the problem. If distance is correct, then this galaxy's brightness becomes an inexplicable anomaly. It shines as if hundreds of millions of stars already burn within it, though by all physics laws they shouldn't be there. The next verification stage was the gravitational lensing hypothesis. According to Einstein's general relativity, a massive lens galaxy in front of the observation object can curve space and work like a magnifying glass, artificially enhancing brightness. The data analysis group rushed to recalculate mass distribution models along the line of sight. If we found an unaccounted lens, the paradox would be solved and the standard model saved. We prayed for this lens. But mathematics is inexorable. Calculations showed that even accounting for all possible lensing effects, stellar population mass in these early galaxies remains beyond limits. We're talking about hundreds of millions of solar masses gathered into compact structure in cosmically insignificant 300 million years. To understand the tragedy's scale, this is like seeing a fully built and populated megapolis 5 minutes after the first stone was laid in the foundation. Here we hit a rigid limitation on construction material amount: baryonic matter. In the early universe, according to the ΛCDM model, matter existed as hot ionized gas. To assemble this gas into stars, gravity needs time. Gas must cool, lose energy, and collapse. This process has a physical speed limit. Gas cannot fall into a gravitational well faster than a certain rate, or radiation pressure will throw it back. Theoretically, in this epoch we should see only the first timid attempts of space to light up. These are so-called population 3 stars. Gigantic short-lived luminaries consisting exclusively of hydrogen and helium. They should be lonely beacons in darkness, not united stellar megalopolises. And certainly their spectra shouldn't contain heavy elements. But Webb sees not just hydrogen clouds, it sees complex structures enriched with oxygen and carbon. Oxygen presence is the control shot to old theory. Oxygen and carbon are born only in dying stars' cores and thrown out during supernova explosions. To saturate a galaxy with these elements, several stellar generations must change. The birth-life explosion cycle takes millions of years. The universe at that moment simply didn't have that much time in reserve to run this cycle, the required number of times. Chronology cracks at the seams. The operator in Baltimore looks at the final report and understands. Technical diagnostics are complete. All telescope systems work properly. Mirrors are perfectly focused. Sensors cooled to near absolute zero. Data transmission proceeds without loss. And it is precisely this machine's flawless work that passes sentence. If the telescope were broken, we could fix it or recalibrate it. But a functioning telescope showing impossible data means the model of creation itself is broken. We tried to blame everything on instrumental noise, statistical fluctuation, anything rather than touch the foundation. But fact is a stubborn thing. We observe maturity where infant emptiness should be. Imagine coming to kindergarten and seeing 3-year-olds defending doctoral dissertations in quantum mechanics. This is approximately the same cognitive dissonance cosmologists worldwide now experience. This discovery moves the problem from engineering to theoretical plane. We can no longer hide behind measurement errors. We face facts. The standard universe evolution scenario taught in universities for the last 40 years doesn't just need clarification. It is fundamentally wrong in its opening chapter. We have bricks, matter, and we have mortar, gravity, but we categorically lack time for construction. Now that hope for instrument error has definitively dissipated, the word passes to theorists. People whose job is explaining the unexplainable enter the case. They must answer a question that seemed absurd just yesterday. How do you create a ready galaxy from nothing in the blink of an eye? And the first answer they'll propose will be connected with objects capable of violating any rules. Monsters that devour space itself. Cosmology's crisis has officially begun. We're entering turbulence where familiar formulas stop working, and Einstein's equations encounter observations they cannot predict. The operator in Baltimore ends his shift, leaving on servers data that will rewrite physics textbooks. Night falls on Earth, but for science, a frightening new era dawns. An era where we perhaps don't understand at all where and when we are. Chapter 4. When mathematics fails. When operators in Baltimore finished their shift, leaving us alone with numbers, silence moved here to theoretical physics auditoriums. Here there is no server humming, only the dry chalk tapping on blackboard and projectors' quiet buzzing. The gravity theorist looks at equations that yesterday seemed unshakable law and feels the ground disappearing beneath his feet. James Webb data isn't just pretty pictures. It is the death knell for the model we've built over half a century. On the projector screen, a cosmological simulation runs. This is our attempt to recreate universe history digitally, using known physics laws. The theorist inputs parameters aged 300 million years after the Big Bang. He presses start, expecting to see the first galaxy's birth. But the screen shows only formless gas and rare dim sparks of first stars. The simulation works flawlessly, but it doesn't show what the telescope saw. The virtual universe is empty while the real one overflows. We've encountered what engineers call a time budget problem, but on cosmic scale, the standard cosmological model, known as ΛCDM, allocates us strict time frames. According to it, our universe's age is 13.8 billion years. This is an enormous period, but it is not infinite. And most importantly, the initial construction stage, according to this model, should be painfully slow. Imagine building a skyscraper. First, you dig a pit, then pour foundation. Wait for concrete to set, and only then, floor by floor, erect the frame. In space, gravity plays concrete's role, and hydrogen and dark matter play bricks' role. To assemble a Milky Way-sized galaxy requires billions of years of mergers, absorptions, and gravitational dance. This doesn't happen instantly. Physics is nature's bureaucracy, and it doesn't tolerate haste. However, objects found by the telescope look as if the skyscraper appeared from nowhere overnight. We call them universe breakers. Looking at these images, the theorist sees structure that doesn't yield to modern galaxies in complexity and mass, but it is located in an epoch when the universe barely emerged from swaddling clothes. This is like planting an acorn, turning away for a second, and turning back to see a century-old oak. Here comes into play the fundamental law the theorist now furiously rewrites on the board, the Eddington limit. Any star or black hole gaining mass emits light. If it devours matter too greedily, outgoing light pressure becomes so powerful, it literally blows food off the table, stopping growth. This is a natural speed limiter built into reality's fabric itself. The Eddington limit tells us you cannot grow faster than a certain rate, even if there is plenty of matter around. But Galaxies Webb saw gained masses of hundreds of millions of suns in time frames physics considers impossible to manage to grow to such sizes in 300 million years. These objects had to constantly violate this limit, continuously absorbing matter faster than radiation resistance allows. The theorist erases another equation from the board. Chalk crumbles, settling as white dust on jacket sleeves, a symbol of entropy in action. He understands either these early galaxies found a way to cheat gravity, or our understanding of gravity in the early universe is wrong. We're trying to cram a billion-year process into a narrow 300 million-year corridor, and mathematics resists. Equations begin outputting infinities, which in physics language means catastrophe. The problem worsens because star formation requires cold. Hot gas doesn't compress, it expands. To ignite a star, a hydrogen cloud must cool. And in the early universe that was hot and dense, cooling is an extremely inefficient process. We simply don't have cooling mechanisms capable of working at such speed. Universe breakers don't just violate schedules. They ignore thermodynamics. On the simulation screen, the theorist tries increasing dark matter density. Virtual galaxies begin forming slightly faster, but still don't manage to reach required sizes by redshift the 14th of March K. The lambda CDM model cracks at the seams. We're used to considering it standard, but now it looks like an outdated locality map, where newly grown mountains and appeared oceans aren't marked. This is that very cosmology crisis whispered about in conference corridors. This isn't an argument about a comma in a formula. This is realizing we have no foundation for understanding creation's first chapters. If galaxies are already mature, then their birth process started much earlier than we thought. But there is nowhere earlier. Behind these galaxies lies only the Big Bang, the wall of flame where no structure can exist. The theorist steps away from the board. It is covered with tensors and integrals, but none gives an answer. Heavy silence hangs in the auditorium. We've encountered a paradox. Objects exist, but according to our laws, they cannot exist. This means either we're measuring time wrong, or some other force acted in the early universe, an unknown catalyst that accelerated matter assembly thousandfold. In attempts to save theory, scientists begin proposing hypotheses they would have dismissed as science fiction just yesterday. Maybe matter didn't assemble slowly, dust speck by dust speck. Maybe the universe already had giant gravitational traps that instantly pulled gas into galaxies. We need a monster capable of devouring matter without regard for the Eddington limit. Light in the auditorium dims, leaving only the screen glow with failed simulation. The theorist understands the solution doesn't lie in classical stellar evolution plane. The answer may hide in dark corners where we're afraid to look. If normal matter doesn't have time to build a house, perhaps the framework was erected by someone else, someone ancient, heavy, and invisible. We're approaching a line where stellar astrophysics ends and extreme states physics begins. To explain the impossible, we'll have to resurrect old, half-forgotten Soviet physicist theories. Theories that these galaxies' seeds were sown not by stars but by space-time folds themselves, twisted into tight knots before the first light ignited. Chalk set aside, equations erased. The standard model couldn't handle James Webb's challenge. Now, to explain what we've seen, we'll have to allow the existence of objects born not from matter, but from the Big Bang's pure energy. We're setting off to search for primordial black holes. Chapter 5. Echoes from the Soviet Past. To find answers to the future's puzzle, sometimes you need to look back, In the Russian Academy of Sciences Institute for Space Research Office on Kaluga Square, it is now dark and quiet behind the windows of night Moscow, a city where physics has always been more than just science. Or astrophysicist stands at the window, but he sees not the prospect, but the depths of time. On his desk lie not James Webb printouts, but yellowed pages of a scientific journal, publication year 1967. At time when the world only dreamed of conquering the moon, two Soviet thought giants, Yakov Borisovich Zeldovich and Igor Dmitrievich Novikov, had already looked where telescopes would reach only half a century later. They formulated a hypothesis considered a beautiful mathematical abstraction, a mind game, for 50 years. But today, looking at impossible data from space, our hero understands this wasn't a game. It was prophecy. We're used to thinking black holes are stellar corpses, a kind of tombstones. First, a star must be born, live millions of years, burn all fuel, and only then, dying, collapse under its own weight. This process requires time the early universe, as we discovered in the last chapter, simply didn't have. But Zeldovich and Novikov asked a bold question. What if black holes can be born without stars? What if they're older than light itself? Picture the first moments after the Big Bang. This isn't emptiness, but a boiling soup of super-dense energy and plasma. In this chaos, matter density is so high that any random compaction, any even most insignificant fluctuation, can be fatal. Gravity at such points becomes absolute. Matter doesn't have time to fly apart. It collapses into itself. This is how primordial black holes are born. For the astrophysicist in this office, this thought changes everything. If Soviet theorists were right, then the universe wasn't a clean slate on which stars slowly wrote their history. No, it was initially mined. Primordial black holes became those very invisible frameworks we so lacked to explain Webb's data. They appeared not after millions of years, but in the first second of creation. Now, look at universe breaker data from this angle. Galaxy JGDSS 14-0. SEM's impossible to us, because we thought it had to assemble itself, atom by atom, overcoming radiation pressure. But if a monstrous gravitational vacuum cleaner in the form of a primordial black hole sat in its center from the very beginning, the game rules change. It didn't need to grow. It was born heavy. These objects acted as the most powerful crystallization centers. Imagine throwing a salt crystal into a supersaturated solution. The stone grows instantly. Similarly, primordial black holes pulled gas from surrounding space onto themselves. They accelerated galaxy evolution thousandfold, allowing hundreds of millions of solar masses to be assembled in timeframes the standard model considers unthinkable. Our astrophysicist rereads Zeldovich's equation. Mathematics here is cruel but elegant. It removes the Eddington limit problem. An ordinary black hole, absorbing matter, chokes on its own radiation that repels food. But a primordial black hole arising from dense plasma could gain mass before space became transparent to radiation. It could feast in the dark while the universe was dark. This explains the mass paradox. Those bright spots James Webb fixes at redshift 14 aren't just young star clusters. They're accretion disks raging around ancient monsters. We see light from matter falling into throats that opened before the first hydrogen atoms were born. This is domestic theoretical school triumph. But this triumph has a taste of alarm. Accepting this hypothesis solves the local task, but creates a global problem. If primordial black holes exist, then the Big Bang wasn't an ideally smooth expansion process. Someone or something had to create these density differences. Where did this lumpiness in the first fraction of a second come from? After all, according to classical theory, the universe should be homogeneous, like pasteurized milk. The astrophysicist lifts his gaze from papers. In the office silence, only an old refrigerator's humming is audible. But in his head sounds the early universe's roar. If we allow primordial black holes existence, we're obliged to admit our beginning picture is wrong. We remove dark matter as the main building material and replace it with myriads of black holes permeating space. This changes everything, from galaxy structure to the solar system's fate. Moreover, calculations show a frightening detail. To create enough such holes to explain Webb's data, the universe had to go through a phase transition of incredible cruelty. This wasn't smooth birth. This was an explosion within an explosion. Space-time broke and twisted into knots, forever sealing energy in gravitational traps. We call these galaxies impossible, but from Zeldovich-Novikov theory's viewpoint, they're the only possible ones. The standard ΛCDM model assumed matter's slow waltz. The telescope showed us gravity's hard rock, and the soloists in this concert were objects we considered only hypothetical ghosts on paper. But if primordial black holes comprise a significant part of universe mass, a question arises: where are they now? They couldn't disappear without a trace. They should be here among us. Thousands, millions of invisible objects wandering between stars, flying through solar systems. Perhaps one such hole is passing through our galactic arm right now, remaining unnoticed. This theory also challenges our understanding of gravity. If the early universe was so overflowing with these objects, then the very concept of dark matter might be an unnecessary entity. We've spent years searching for WIMPs and axions, mysterious particles to explain excess mass. The answer might have been on the surface. Mass is hidden not in exotic particles, but in countless black holes we simply can't see. The astrophysicist knows that in science, you pay for every answer with two new questions. If primordial black holes' gravity is so strong, why didn't it tear the early universe apart? Why didn't space collapse back into singularity immediately after birth? Something held this chaos in balance. Some force opposed this monstrous gravity. We found the monster that built galaxies. We justified telescope data, but doing so, we questioned the very foundation of physical laws. If dark matter doesn't exist or looks completely different, then our gravity equations are incomplete. And while dawn breaks in Moscow, at CERN on Europe's other end, theorists begin suspecting the error lies not in space, but in Isaac Newton's formulas. Chapter 6. The Death of Dark Matter. Suspicions born in Moscow office's silence find their frightening confirmation here. In kilometers of underground tunnels, on Switzerland and France's border. While astrophysicists search for black holes in the sky, theorists at CERN have hunted the ghost right beneath our feet for decades. We built humanity's most complex mechanism, the Large Hadron Collider, to catch a dark matter particle. Through a gravity theorist's eyes, this detector hall looks not like engineering triumph, but like a monument to our delusion. We call these hypothetical particles WIMPs, weakly interacting massive particles. Supersymmetry theory promised us detectors would record their traces, but year after year, monitor screens show only perfect sterile emptiness. Absence of results in physics is also a result. often louder than discovery. If we see no dark matter particles either in space or underground traps, we're obliged to ask a question that makes any physics professor's spine chill. What if there is simply nothing to catch? What if we invented invisible mass only to save our familiar equations? The James Webb Telescope poured oil on this doubt fire. Observing early galaxy rotation, we expected to see influence of enormous dark matter halos that, according to the standard model, should hold stars together. But data coming from the early universe look strange. Galaxies behave as if no hidden mass exists in them, yet they don't fall apart. Here enters a theory long considered heresy in respectable scientific society: modified Newtonian dynamics. The idea is simple and simultaneously destructive. Dark matter doesn't exist. Error lies not in missing mass, but in the law of universal gravitation we've considered unshakable since Newton's apple fell. The hypothesis's essence is that gravity isn't a constant. At huge accelerations, like on Earth or in the solar system, Newton's and Einstein's laws work flawlessly. But at galaxy outskirts, where accelerations are infinitesimal, game rules change. Gravity doesn't weaken with distance as fast as textbooks predict. It remains tenacious, holding stars without any outside help. Physicists introduced a special parameter, acceleration threshold, equal to 1.2 Fe meters per second squared. This is an incredibly small quantity, impossible to notice in Earth laboratory conditions. But at galactic scales, precisely this threshold separates classical physics from the reality Webb possibly sees. For a theorist standing before a board with tensor equations, this is a real nightmare. Recognizing MOND means recognizing that Einstein's general relativity, our main tool for understanding the universe, is only a special case of deeper and stranger truth. This is like learning that the map you've sailed by all your life is correct, only within your harbor's limits. The paradox is that James Webb sees galaxies that perfectly fit modified dynamics predictions. Those very impossible early galaxies that wouldn't have time to accumulate dark matter become quite natural in MOND's framework. They don't need hidden mass to quickly assemble into structures. Space-time fabric itself works for them, strengthening gravity. However, this medal has a flip side we cannot ignore. If we rewrite gravity laws to explain distant space, our physics here in the solar system begins to crumble. Planetary trajectories, satellite movements, even GPS operation. All this is built on Einstein's equations. Attempting to fix galaxies might break our own stellar system. We find ourselves in intellectual splits. On one hand, Webb's data screams that the old model doesn't work. On the other, proven physics reliability that lets us launch rockets. The theorist looks at graphs and understands we're trying to stretch the same formula over two completely different worlds. The world of planets and the world of galaxies, and this formula cracks at the seams. The situation worsens when we look at cosmic microwave background radiation. The model without dark matter poorly explains how matter distributed in the first 300,000 years. If we reject dark matter, we need to invent something in return that performed its role in the early universe. It turns out we're changing one puzzle for another, even more complex. But fear of new physics shouldn't stop us. Science history knows many examples when unshakable truths crumbled under fact's pressure. Once we added epicycles to explain planetary motion around Earth until we understood Earth itself rotates around the Sunday. Perhaps dark matter is our modern epicycles. Data obtained in 2024 indicates that so-called galaxy pairs rotate around each other faster than dark matter theory predicts. but in exact accordance with Mond. This observation cannot be dismissed as instrument error. This is a direct blow to the standard cosmological model's foundation, delivered with sniper precision. If gravity truly changes its properties at large distances, this questions another fundamental concept: accelerated universe expansion. We explain it with dark energy, another invisible entity, but within modified gravity framework. Expansion might prove an illusion caused by our misunderstanding of how light interacts with space. We stand at a crisis threshold, extending far beyond gravity alone. If our rulers are curved, how can we measure the universe's size? How can we speak of its age? We're approaching a problem that frightens astronomers even more than dark matter's disappearance. This problem tears space-time fabric itself, and its name is Hubble tension. Chapter 7. The Hubble Crisis. Hubble tension. This term sounds dry, almost technical, as if discussing electrical grid malfunctions. But in this conference hall, where two diverging graphs freeze on a huge screen, you feel completely different tension. This is panic electricity here, in silence broken only by projector humming. The fate of our entire cosmological history is decided. If we're wrong here, we don't know the most important thing about the universe: how fast it is dying. Look at this graph. Two lines, red and blue, should intersect at one point. This is reality consistency law. If you measure table length with a tape measure, then with laser rangefinder, numbers must match. But on screen these lines diverge in different directions, like rails before a train wreck. This gap between them isn't just calculation error. This is the abyss into which all modern physics falls. We're talking about Hubble's constant, the number describing our universe's expansion rate. This is perhaps the most important parameter in cosmology. Knowing it, we can rewind the film backward and calculate creation's exact age. For a long time, we thought we knew this number with sufficient precision. But when our instruments became perfect, the universe played a cruel joke on us. It gave us two different answers to the same question. The first answer comes from the early universe. We look at cosmic microwave background radiation, echo of the Big Bang, cooled over 13+ billion years. Planck's satellite measured this glow with incredible precision. Based on the Standard Model, we predict how fast the universe should expand today. Planck's answer is unambiguous: 67.5 kilometers per s-econd per m gigaparsec of space. This is the number 67, reliable foundation. It fits perfectly into ΛCDM theory with dark matter and dark energy. The question seemed closed. But there is a second measurement method: the late universe. We take a ruler and measure distance to neighboring galaxies here and now using pulsating Cepheid stars, and type 1, a supernova explosions. These are our standard candles, beacons whose brightness we know for certain. And here, catastrophe begins. When astronomers led by Nobel laureate Adam Rees measured expansion rate by supernovae, they got not 67. Their result, 73, sometimes 74 kilometers per s per m gigaparsec. The difference seems small, only 9%. But in precise physics world, this isn't error. It is blatant contradiction. Imagine measuring your child's height. Doctors studying genetics and birth analyses predict, when grown, he'll be 1.4 meters tall. This is early universe forecast. But when the child turns 10, you take a ruler and see he is shot up to 1.6 meters. You change rulers, call a medical council, but fact remains. The child grew faster than biology laws allowed. The same happens with space. For a long time, skeptics hoped the problem lay in our rulers. Maybe Hubble telescope wasn't precise enough. Maybe we incorrectly calibrate Cepheid brightness in distant galaxies dusted with interstellar gas. Astronomers prayed this was systematic error. They waited for James Webb's launch, like a judge who would come and say, "Relax, you just miscalculated." But James Webb brought no peace. On the contrary, it became chaos messenger. Thanks to its infrared vision, it could see individual Cepheids through dust with unprecedented clarity. It double-checked Hubble's data and rendered verdict. Measurements are correct. Astronomers didn't err. Error lies not in telescopes or observers' eyes. Error is sewn into universe structure itself. This discrepancy's statistical significance reached 5 sigma level. In science language, this means random coincidence probability is 1 chance in 3.5 million. This is discovery's gold standard. We can state with full confidence the universe expands faster than it should, and we have no idea why. Someone or something presses the gas pedal, and this something doesn't fit any equation. This discovery puts us before frightening choice. Either our cosmic microwave background measurements are wrong, extremely unlikely given Planck's precision, or, much more terrifying, our universe evolution model is fundamentally mistaken. Perhaps some exotic form of early dark energy existed in the early epoch that disappeared, but managed to give the universe additional push. Or maybe we don't understand gravity's nature at all. If modified Newtonian dynamics we discussed earlier is correct, it should also influence expansion, but even Mond struggles to explain such a gap. We find ourselves where two impeccably precise reality maps, overlaid on each other, don't match. This isn't just a map spot. This is a crack running through the entire foundation. The Hubble constant value gap means we cannot precisely say our universe's age. If Planck is right, it is 13.8 billion years old. If supernova observations are right, it might be 1 billion years younger. But wait, we just saw galaxies that look mature only 300 million years after the beginning. If the universe is actually younger, the impossible galaxies paradox becomes even more unsolvable. We're cornered. On one side, James Webb shows us galaxy elders at time's dawn, requiring the universe to be older. On the other, expansion measurements suggest the universe races faster than we thought, hinting it is younger. These facts don't just contradict each other, they try to tear logic to shreds. We're trying to assemble a puzzle with pieces from two different boxes. Precisely at such moments, when official science reaches deadlock, forgotten rejected theories emerge from shadows. Ideas laughed at for half a century suddenly seem like the only life ring. If space cannot stretch at different speeds, perhaps the problem isn't space. What if light itself, carrying information, deceives us? Hubble tension isn't just arguing about numbers. It is an alarm bell sounding throughout the universe. It tells us, you are looking at the world through curved glass. And to understand what is really happening, we perhaps must abandon cosmology's most sacred cow, Big Bang Theory as we know it. After all, if the ruler changes length during measurement, then reality itself is unstable. Chapter 8. The Return of Tired Light. In astrophysics observatory libraries, they increasingly pull old early 20th century works from shelves. There, on yellowed pages, lies a hypothesis buried before Gagarin's flight. It was beautiful, but not correct. At least so, we thought until today. But now, when the universe cracks at the seams, it is time to dust off tired light ideas. In Institute for Space Research Library silence, among shelves with yellowed volumes. Tablet screens seem like alien artifacts. Astrophysicists come here not for new data, but for old ideas. When modern equations lead to deadlock and Hubble tension tears cosmology apart, one must seek answers in archives we considered closed forever. On screen before us is a 1929 article. Its author, Swiss astronomer Fritz Zwicky, was known for his foul temper and genius intuition. He proposed redshift explanation before Hubble became an icon. Zwicky claimed, "Galaxies aren't flying away from us. Space is static. Light simply tires, overcoming billions of light years." Tired light hypothesis sounds deceptively simple. A photon flying through the abyss doesn't move in perfect emptiness. It interacts with quantum fluctuations, gravitational fields, or even intergalactic dust. In this struggle, it loses a tiny fraction of its energy. And since light energy directly relates to its frequency, energy loss means spectrum reddening. For a decade, this idea was considered scientific heresy. If light truly aged, losing energy in collisions, distant images would be blurred like view through frosted glass. But Hubble telescope, and now James Webb, shows us distant space with razor sharpness. The case seemed closed. But 2023 data forced us to return to this corpse and find it had a pulse. A new model, published amid Webb data crisis, offers a frightening hybrid. It is called CCC-FETL, combination of changing fundamental constants and that same tired light. This theory claims we erred in interpreting redshift exclusively as Doppler effect, recession speed. Part of this shift is light's age itself. The astrophysicist peers at recalculated graphs, and cold runs down his spine. If we apply this hybrid model to James Webb data, universe timescale stretches like rubber band. Those very impossible mature galaxies we saw at 300 million year mark turn out not to be infants at all. They're where they belong. But our time ruler was broken. This model's mathematical conclusion sounds like a sentence for all modern chronology. Our universe's age isn't 13.8 billion years. According to calculations, we're 26.7 billion years old. The universe instantly ages twice, right before our eyes on these tablet screens. 26.7 billion years. This figure solves the seemingly unsolvable problem. If the universe is twice older, universe-breaker galaxies had extra billions of years for formation. No Eddington limit violation, no mysticism. Stars managed to ignite, black holes to gain mass. We were just looking at a clock running twice fast. But solving one puzzle creates catastrophe in physics foundation. Accepting this model means the Big Bang as we understand it, as a single moment of expansion beginning from singularity point, might not have happened at all. Or it occurred so long ago and differently that we see no traces. Cosmic microwave background radiation, which we considered birth echo, becomes simply light-tired to microwave state. For a theorist, this resembles earthquake. We built all astrophysics on expanding space foundation. If space is static and only photon energy changes, dark energy isn't needed. Accelerated universe expansion is illusion. Optical deception caused by not understanding light nature at cosmological distances. EKI library becomes almost physically stuffy. We're used to thinking we live in an exploding, dynamic world. But Tired Light model paints universe as infinite, calm ocean, where light slowly fades, traveling between eternal galaxy islands. This returns us to Einstein's ideas, who dreamed of precisely such stationary universe until life's end. However, this salvific theory has its price, and it is high. For tired light mathematics to match supernova observations, we must allow another heresy. Physics laws themselves must change. CCC in theory's name means covariance of coupling constants. This means the force with which particles attract or repel wasn't constant throughout history. We approach a brink where certainty ends. If universe age is 26 billion years, fundamental constants like light speed, electron charge, or Planck's constant could drift. What we consider nature's immutable laws might be only temporary rules operating in our epoch. The astrophysicist closes the article, but cannot close the question hanging in air. We tried saving Standard Model by adding black holes. Didn't work. We tried changing gravity. Didn't help. Now we're ready to double creation's age and cancel the Big Bang. This resembles panic in a burning house when tenants throw most valuable things out windows, trying to escape. Fritz Zwicky's hypothesis, risen from oblivion after 90 years, gives us breathing room. It explains how galaxies manage to grow, but it requires us to admit reality's foundation. Constants holding matter together is unstable. And if we dig deeper into this rabbit hole, we might discover not only light changes, but vacuum structure itself. In attempting to explain one telescope image, we began rewriting everything's history. 26 billion years of evolution means we see not time's beginning, but only infinite cycles' middle. And the next step in this investigation will lead us into matter's heart, where physical laws themselves are born. Chapter 9. The Quantum Crisis. Accepting universe age hypothesis of 26.7 billion years isn't just changing a number in textbooks, it is changing fundamental paradigm. If we stretch timescale twice to explain mature galaxies' existence, we inevitably face foundation stability question. The gravity theorist looks at screen visualizing quantum field and understands cosmology salvation price might be prohibitively high. We preserved galaxies, but perhaps lost physics law's eternity. For a theoretical physicist, watching quantum vacuum simulation resembles looking into reality's engine room. Emptiness on screen isn't empty, it boils. Virtual particles are born and annihilate within nanosecond fractions. Here, in this microworld chaos, rules are determined for gigantic galaxies. And the main rule we've been certain of for centuries states: physical constants are unchanging. Light speed, electron charge, gravitational constant. These are unshakable pillars supporting creation's edifice. But what if this foundation shifts? We're used to considering light speed an absolute quantity. 299,792,458 m/s. Engrave this on stone, and in a billion years the number will remain the same. However, new cosmological models trying to reconcile James Webb data with reality hint at a frightening possibility. In the early universe, light could move differently, and this concerns not only light. Among all numbers describing our world, one evokes scientists' special awe: fine structure constant, denoted by Greek letter alpha. It characterizes electromagnetic interaction strength. Simply put, alpha determines how firmly electrons hold to atomic nuclei and exactly how matter interacts with light. Its value is approximately 1/137th. For a long time, this number was thought carved into universe structure once and forever. However, suspicions about alpha's inconstancy arose before Webb's launch. Analysis of light from distant quasars active galactic nuclei located billions of light years from us showed strange anomalies in absorption spectra. Chemical element lines were shifted as if in distant past electromagnetism worked slightly differently. James Webb Telescope, with its incredible infrared sensitivity, allowed peering into this problem with frightening clarity. If we allow the universe is twice older than we thought, we give constants much more time for so-called drift. The theorist sees in equations not static numbers but time-dependent functions, even tiny fine structure, constant changes, just a few thousandths of a percent, have catastrophic chemistry consequences. Atomic electron shells change configuration, and familiar chemical reactions become impossible. To understand threat scale, look at what we're made of: carbon, life's basis. Its synthesis in stellar cores occurs thanks to amazing nuclear resonance coincidence known as triple alpha process. 3 helium nuclei merge into carbon only because energy levels are tuned perfectly precisely. If fine structure, constant changes even 0.5%, this resonance disappears. Stars stop producing carbon. Universe becomes sterile. The theorist overlays observation data on constant drift model. Graphs show that in the early epoch Webb now studies, physics could be hostile to life as we understand it. This brings us to the so-called anthropic principle. We observe precisely these constant values, not because they're the only possible ones, but because with other values, no one would be here to conduct observations. We're survivors in fundamental physics lottery. But the anthropic principle is a philosophical dead end for a researcher. To say it just happened this way means abandoning cause search. Webb's data about early galaxies that look too mature might indicate past interactions were stronger. Enhanced gravity or altered electromagnetism could work as catalysts, allowing stars to ignite faster and galaxies to assemble into giant structures in time frames unthinkable for modern physics. This solves universe breaker puzzle but opens Pandora's box. If physics laws evolve with universe, where is guarantee they've stopped developing? Looking at the calm night sky, you can be sure tomorrow's sunrise. But a theorist looking at tensor equations understands. If constants continue drifting, one day the proton might become unstable, and all universe matter will simply decay. The idea of changing nature laws returns us to time's nature question itself. In model with drifting constants, time stops being just a ruler measuring history. It becomes an active participant, changing matter properties. 26 billion years isn't just a long period. It is a gigantic laboratory where universe sorted through various physics options until reaching current temporarily stable state. Visualization on theorists' screen changes. Now it is not just boiling vacuum, but complex space-time topology. If constants change cyclically, perhaps universe history itself isn't a straight line from Big Bang to heat death, but a giant wheel. The idea that physics laws cool and crystallize with time suggests something else existed before our beginning. We tried explaining one telescope's anomalies and concluded our physics is only a momentary snapshot in infinite nature law mutation process. Carbon, oxygen, starlight, all this exists thanks to fragile balance that was different in past and will become different in future. James Webb looks into past and sees there not only other galaxies, but other physics. This frightens because it deprives us of reference point. But if physical laws change, then mechanism must exist controlling these changes. Some law standing above Einstein's and Sharp-Feidinger's equations. Theorists begin seeking answers in higher order geometry. Perhaps what we perceive as constant change is projection of multidimensional processes onto our three-dimensional reality. Like shadow of rotating object changes length, our constants change as universe moves through higher dimensions. In this context, universe age loses familiar meaning. If compression and expansion cycles change physics, then 13 or 26 billion years is only current eon duration. We approach Nobel laureate Roger Penrose's concept. What we considered absolute beginning, Big Bang, could be only transition moment when old dying universe passed baton to new one. Quantum foam on theorists' monitor continues infinite boiling. Particles arise from nowhere and disappear into nothing. This reminds us nothing is eternal, even conservation laws themselves. If Webb truly saw traces of previous epoch encrypted in early galaxies' light, we'll have to rewrite not only astronomy textbooks, but the very concept of world creation. Chapter 10. The Cyclic Universe. If fundamental constants truly drift as we suggested last chapter, then linear time concept itself begins cracking its seams. We're used to thinking of universe as arrow shot from Big Bang bow toward heat death, but early galaxy maturity Webb recorded hints this arrow flies not straight, but in circle. What we take for incredibly fast evolution might be heredity. Look at this diagram on monitor. These aren't just abstract geometries. They're Penrose diagrams describing space-time structure where infinity is packed into limited form. Here we find answer to question tormenting astrophysicists. How did infant galaxies manage to age in couple 100 million years? The answer Sir Roger Penrose offers frightens with its simplicity. They didn't age. They were born with past memory. Theory known as conformal cyclic cosmology claims our Big Bang wasn't everything's beginning. It was only transition moment, a kind of mountain pass between previous universe's death and ours birth. Penrose calls these life cycles eons. According to this model, we live in just one of infinite succession of eons, replacing each other in eternity. To understand this process physics, we need looking into our own world's deep future. After trillions of years, all stars will burn out. Black holes, having absorbed matter remnants, will evaporate. Protons will decay. Universe will become infinitely cold and empty photon ocean. And precisely at this moment, at absolute entropy point, mathematical miracle occurs. For photon flying at light speed, time doesn't exist. It has no rest mass, meaning no distance concept. When nothing remains in universe except light, scale concept loses physical meaning. Enormous, cold, and empty future universe becomes mathematically identical to hot, superdense singularity point. End becomes beginning. This is called conformal transition. Previous eons boundary stitches with current boundary. But this stitching doesn't pass without trace. Previous universe was filled with gigantic structures, and their ghosts can cross this barrier. Perhaps James Webb Telescope sees precisely them now. Looking at time's dawn, Roger Penrose claims we can find direct evidence of this process on cosmic microwave background map. He calls them Hawking points, anomalous zones with elevated temperature that, according to calculations, are traces of supermassive black hole evaporation from previous eon. These past titans died, but their gravitational death cry imprinted in our reality's structure. Imagine supermassive black hole in past universe drew entire galaxy clusters into itself over billions of years. At time's end, all this colossal energy was thrown back as Hawking radiation. This concentrated energy flow created powerful gravitational wave that overcame Big Bang moment and entered our world. In our young universe, these Hawking points became attraction centers. They worked as ready gravitational wells. Matter after Big Bang wasn't distributed evenly as standard model states. It flowed into channels laid by previous cycles' dead black holes. This explains paradox that defeated all other theories. This is why James Webb sees monster galaxies where they shouldn't be. Object JGDSS 14-0 didn't have to gather such mass. It built on previous world's ruins foundation. We see not acceleration miracle, but construction debris from past stellar civilization. This hypothesis elegantly solves time problem. We don't need stretching our universe's age to 26 billion years like tired light theory. We don't need breaking Newton's laws like Mond. Universe is truly 13.8 billion years old. But seeds it grew from are eternal. This changes cosmology's very philosophy. Looking at schematic images of compressing and expanding eons, I understand why this idea causes such resistance in scientific community. It deprives us of uniqueness. We're not creation's crown, but just another iteration. But Webb's data is inexorable. Standard model required dark matter to assemble galaxies, but even with it, process goes too slowly. Cyclic cosmology gives us necessary head start. However, if matter decays, how does structure information preserve? Penrose speaks of gravitational waves, but there is more radical view. If universe is cyclic process, then somewhere must be hard drive, where data records before system reboot. Information cannot disappear without trace. This is prohibited by quantum mechanics laws. But we approach understanding limits. If Webb galaxies are past echoes, then space-time fabric itself must possess memory. We're used to considering vacuum emptiness, but in cyclic universe context, it more resembles film on which movie is recorded. And now we're watching this movie, thinking it is reality. This leads us to thought that our world's three-dimensionality might be illusion. If past eon information survived and transmitted to us, it had to pass through Big Bang bottleneck, where space was compressed to two-dimensional surface. What we see through telescope might be holographic projection of data recorded on past horizon. Diagram on theorist's screen dims, leaving us alone with this thought. We sought telescope calibration error and found indication that our very reality is secondary product. James Webb looks at universe edge and sees pixels our creation consists of, and these pixels become increasingly grainy. Chapter 11. The Holographic Prison. In Baltimore Mission Control's sterile silence, mission operator looks at monitor where image pixels merge into gray haze. Previous thought that our reality might be only secondary product, or past cycle echo forces different look at this technical noise. Usually such interference is blamed on detector thermal fluctuations or cosmic rays. But today, noise graph looks frighteningly ordered. This isn't chaos, this is structure. Operator increases scale of most distant galaxy image accessible to James Webb. According to Einstein's classical geometry, space-time should remain smooth at any magnification level. Like perfect sphere stays round no matter how much you enlarge it. But at extreme distances, at very edge of observable universe, image begins graining. We hit fundamental resolution limit of reality itself. Main question now hanging in this dark room's air. Where is information describing our entire universe stored? If we accept Cycle's idea, or even just try understanding black hole structure, we encounter library paradox. Intuition tells you book quantity, fitting in library depends on building volume. Bigger hall, more information. But black hole physics tells us opposite. In 70s, physicist Jacob Bekenstein and Stephen Hawking discovered an anomaly that overturned matter understanding. Studying black hole entropy, they derived formula according to which black hole information capacity depends not on its volume, but on its surface area. Event horizon area. Imagine filling room with air, but molecule quantity depends not on cubic meters of internal space, but on square meters of wallpaper on walls. This discovery led to formulating so-called Bekenstein bound. It states maximum information amount that can be contained in any limited space region exists, and this limit is strictly proportional to area surrounding this volume. This means inside space cannot contain information. It is all recorded on its boundary, like on two-dimensional film. Thus was born holographic universe concept, later developed by Leonard Susskind and Gerard Hooft. If all black hole information stores on its surface, and universe itself is mathematically described by similar equations, then our three-dimensional world is just hologram, projection of data recorded on remote two-dimensional screen. Baltimore operator now looks not into space depths, but at this very screen. For observer inside system, this illusion is impeccable. You feel volume, depth, can move forward and back. But from fundamental physics viewpoint, third dimension doesn't exist. What we perceive as planetary gravity and ourselves is result of complex quantum field interference projected from universe boundary. We're movie characters who gained consciousness and try understanding why film is flat. James Webb, looking back 13.5 billion years, actually looks at this event horizon from inside. And anomalies we see, those very impossible early galaxies, might be compression artifacts. Information density in early stages was colossal. What we took for physical objects violating growth laws might be broken pixels or projection errors when trying to unfold three-dimensional image from dense data array. This explains how information survives at universe death. What we discussed in cyclic cosmology context, when three-dimensional space collapses or disperses, data doesn't disappear. It remains recorded on two-dimensional boundary. Holographic principle solves memory storage problem between eons. Universe hard drive isn't in center but on periphery, where time and space lose familiar meaning. On mission control monitor screens, this theoretical concept gains frightening visualization. Deep field spectral analysis shows strange correlations in noise that cannot be random. Some physicists call this holographic noise, space-time metric itself trembling. This resembles approaching television screen too closely, and seeing announcer face consists of glowing dots. Our world's resolution is finite. Smallest possible length unit is Planck length, comprising 1.6 Fe10 Fe meters. Smaller than this size, no geometry exists. If universe is hologram, then each pixel on its surface has area equal to Planck length squared. And now we see hints that Webb touches this detail limit. Operator inputs recalibration command, hoping to remove graininess, but it remains. This fundamental limitation puts cross on infinity. If space is discrete, if it consists of information bits, then it can be computed, then it can be hacked, or even more frightening, it can hang if data flow exceeds channel capacity. Holographic universe concept turns astrophysics into information science. Black holes become not just matter devourers, but nature's most efficient hard drives. Abnormally massive galaxy at Webb's observation edge might be simply area with increased data recording density on horizon. We're trying to apply Newton's and Einstein's laws to what is essentially program code. This realization causes scientists not delight, but cold existential horror. If we're projection, then who or what is light source? And how stable is this projection? Hologram exists only while information carrier remains stable. Any horizon damage on universe boundary would instantly distort or destroy our three-dimensional reality here in center. Looking at frozen graphs, operator understands what we considered vacuum, empty stage for star movement, is actually complex, densely packed structure under colossal tension. Webb's data shows we live not in empty space, but inside information crystal. And any crystal has stress points where it can crack. Chapter 12. The Vacuum Catastrophe. If space isn't emptiness, but physical medium with discrete structure, then it can change its aggregate state. Like water turns to ice, vacuum can undergo phase transition, and those anomalies, impossible matter clumps we see at time's dawn, might be first signs that our ice begins melting, or conversely, freezing definitively. In Theoretical Physics Center laboratory, it is quiet, only sound, barely audible crackling of cooling equipment. Theorist observes simple physical experiment on table. Supercooled water drop instantly becomes ice from one touch. Liquid becomes crystal. Chaos becomes order. This is phase transition. If we accepted previous chapter's conclusion that space has structure, that it is discrete and hologram, like we must make next frightening step. Any physical structure has aggregate states, and like water can freeze, cosmic vacuum itself can suddenly change its fundamental properties. We're used to considering vacuum emptiness, zero reference point. But quantum field theory tells us opposite. Vacuum is boiling energy ocean, permeated with Higgs field. This field, like thick molasses, slows elementary particles, endowing them with mass. Without Higgs field, electrons would fly at light speed, and atoms would never assemble into matter. Current universe state we observe through James Webb Telescope depends on what energy level this field occupies. Imagine ball lying in valley bottom. It is calm, stable. This is what physicists call false vacuum. Problem is our valley might not be deepest. Standard model calculations, refined by CERN data and newest distant space observations, show troubling picture. Top quark mass and Higgs boson mass are in such ratio that makes our vacuum state metastable. This means behind neighboring hill lies another, deeper lowland, true vacuum state, with minimal energy. In classical mechanics, to reach that deeper valley, ball needs rolling over mountain, requiring enormous energy. But in quantum world, different law works. Tunneling. Particle needn't climb mountain. It can pass through it. Higgs field can collapse into lower energy state at any space-time point. Looking at early universe anomalous data, theorist wonders, aren't those very universe breakers? Galaxies with impossible density and brightness. Evidence that somewhere this process already tried beginning. Density fluctuations we see at redshift 14 look like microcracks in freezing ice. False vacuum decay scenario is absolute catastrophe limit. If this phase transition occurs at some universe point, new physics bubble arises. Inside this bubble, Higgs field takes new value. Nature laws we're used to will be instantly rewritten. This bubble wall will expand in all directions at light speed, 299,792,458 m/s. You cannot run from it, and you cannot learn about it beforehand. No signal can outrun decay front to warn us. If such bubble arose billion years ago in distant galaxy, it already races through space, devouring space. For observers, this will look like instant being shut down. In 1 nanosecond you look at stars. In next your atoms decay because chemistry allowing their existence no longer works. Inside true vacuum bubble. Matter as we understand, it will collapse under monstrous gravity action or scatter into dust. Protons become unstable, stars, planets, observers. Everything will be annihilated and reassembled into completely different, unknown structures. This isn't just world's end, it is physics itself ending. Theorist writes metastable vacuum lifetime equation on board. Numbers are reassuringly large, 10 Fay years, but this is statistics. In quantum world, probability never equals 0. Event can happen through eternity, or can happen right now while you hear this sentence. Webb's data adds frightening variable to this equation. If early universe was as dense and hot as impossible galaxy images show, thermal fluctuations in that epoch could provoke local vacuum decays. Perhaps our universe survived miraculously. Or even stranger, we live inside bubble that devoured previous universe. This returns us to cyclic cosmology idea, but with much harsher scenario, not smooth rebirth but violent regime change. Those anomalies, bright spots at time's dawn that standard model cannot explain, might be scars from collision of different vacuum bubbles. Astrophysicists seek dark matter. Try explaining expansion rate, argue about Hubble constant. But theorist understands all these arguments resemble discussing furniture arrangement in house whose foundation stands on quicksand. If Higgs field is unstable, all our knowledge is only description of temporary lull before storm. In laboratory, ice finally bound water. Crystalline lattice froze. Theorist understands our world's beauty. Stars, galaxies, life is conditioned precisely by this Higgs field fragile tuning. We exist only because universe stuck in wrong false state, allowing atoms not to decay. We call this fine-tuning, but from cold mathematics viewpoint, this looks like system error. Error nature will try correcting sooner or later. And James Webb Telescope, looking ever deeper into space structure, perhaps found not our birth beginning, but countdown timer. Chapter 13. The Impossible Balance. Ice that bound laboratory in our mental experiment isn't just phase transition metaphor. It is illustration of fundamental conditions fragility in which we exist. When Baltimore operator, Geneva theorist, and Moscow astrophysicist look at Webb's summary data, they see not scattered anomalies, but unified, frightening pattern. All strangeness, from impossible early galaxies to expansion rate discrepancy, points to same breakpoint. For a long time, physicists comforted themselves thinking universe is built reliably like Swiss watch, but infrared telescope data forces admitting we live not in clockwork mechanism but on powder keg where fuse has smoldered for 13.8 billion years. Main question of this chapter sounds like verdict. Why does our world exist at all, if according to quantum mechanics, it should have torn itself apart in first instant? At this crisis center stands number. Physicists call science history's biggest mistake. We're talking about cosmological constant or lambda, that very force we're used to calling dark energy, invisible spring, pushing space apart and making universe expand. Quantum field theory allows calculating what vacuum energy should be, and when theorists make this calculation, they get colossal quantity. However, when we look through telescopes, we see actual expansion rate is infinitesimally small compared to calculations. Gap between theory and observations comprises 10 Fe. This is 1 with 120 zeros. Contemplate this scale. If you miscalculated observable universe mass by 120 orders, you wouldn't find even one atom. This monstrous imbalance means one thing. Compensation forces act in vacuum structure, damping quantum field, boiling almost to zero, leaving only tiny tail. Precisely this microscopic remainder, that very lambda we observe, allows galaxies to exist. Were this energy slightly larger, it would blow apart matter before first stars could ignite. Were it slightly smaller, universe would collapse back into point. We call this fine-tuning problem. Imagine throwing dart at target atom, sized on observable universe's other end, and hitting bullseye. Such coincidence probability approaches zero. And yet, here we are, until Webb's launch. Many considered this simply happy constant, number sewn into creation settings once and forever. But Webb telescope, peering into dawn epoch, destroyed the stability illusion. Those very galaxy universe breakers that formed too quickly and became too massive are direct proof that in past, game rules were different. If lambda were unchanging, matter simply wouldn't have enough gravitational force to assemble so quickly into structures, despite space expansion. Analysis of these ancient giants' distribution hints at frightening possibility. Dark energy isn't constant. It is dynamic. This isn't frozen number, but living, changing field. Astrophysicists use term quintessence to describe such dark energy form that can change density with time, and graphs on our heroes' screens show this density grows. This explains early galaxy paradox. Perhaps in young universe, dark energy was weaker, allowing gravity to work more efficiently and create monsters like JGDSS 14-0. But today, pendulum swung the other way. If lambda is dynamic, there is no guarantee it'll stop at current value. We drift toward unknown. Look at data through gravity theorist eyes. If dark energy strengthens, this leads us to Big Rip scenario. Over time, vacuum repulsive force becomes so powerful, it overcomes galaxy cluster gravity. Then it'll tear apart galaxies themselves, then stellar systems, planets, and finally atoms. Space-time will be torn to shreds. Here lies Hubble tension solution. Expansion rate measurement discrepancy we discussed earlier isn't instrument error. It is recording that we live in universe with accelerating acceleration. James Webb effectively documented process where creation vehicle gas pedal begins pressing to floor. Fine-tuning problem transforms from philosophical curiosity into existential threat. If fundamental constants aren't rigid frame beams but movable levers someone or something switches, then our existence is temporary anomaly. We arose in narrow opportunity window when field parameters accidentally coincided to permit life. On monitors at EKI, CERN, and Baltimore, same picture emerges. Galaxy distribution structure on superdeep images doesn't look chaotic. It resembles structure under colossal tension. This looks like metal before tearing or dam with first microcracks. Data screams instability. Anthropic principle states, we see universe thus, because only in such universe could we appear. But it says nothing about how long this state will last. Heat death that classical thermodynamics prophesied is long, boring agony. What Webb hints at is much faster and crueler finale. Vacuum phase, state change, or dark energy critical growth can nullify history instantly. Now becomes clear why mission operators feel cold tension. They sought history's beginning, hoping to see Genesis book's first lines, and found warning perhaps on Apocalypse's last pages. Those impossible mature galaxies at darkness edge are monuments to epoch when physics was different and harbingers of epoch when it'll change again. We're used to thinking nature laws eternal, that light speed, gravitational constant, and electron charge are carved in stone. But stone crumbles. James Webb showed us a universe that doesn't just expand, but evolves at fundamental level. And in this evolution, humanity is only accidental passenger who jumped into car second before train derails. In this silence uniting laboratories worldwide, new understanding is born. We're not creation crown. We're witnesses to grandiose cosmic glitch, equation error that allowed us momentarily to realize ourselves. Our task now isn't just observing, but trying to understand this mechanism's logic while we still have time. While camera slowly retreats, turning our planet into barely distinguishable pale blue pixel against infinite blackness. I remember how we began this journey. We sent James Webb Telescope to Lagrange point L2, 1.5 million kilometers from home, with one goal: to see dawn. We wanted finding moment when first light ignited in universe, confirm our equations, and rest easy. But space isn't obligated to meet our expectations. Instead of infant universe, we saw mature giant structures where emptiness should be. Object JGD's S14-0 and other universe breakers became not just anomaly. They became sentence for standard cosmology model we've built last half century. We encountered facts impossible to ignore. Redshift over 14 masses of hundreds of millions of suns, and oxygen presence where barely cooled hydrogen should be. These aren't calibration errors. This is evidence that either our 13.8 billion year timescale is wrong, or physics laws themselves mutate with time. We passed through hypothesis labyrinth. We saw how Penrose mathematics draws eternity cycles, where one universe's end becomes another's beginning. We glimpsed abyss, where primordial black holes, predicted by Zeldovich, could assemble galaxies in instant. We even allowed frightening thought that light might tire, and reality foundation crumbles, obeying holographic principle. Each answer is more frightening than the question because it takes away stability illusion, realizing we live in false vacuum state, or that cosmological constant lambda differs from quantum theory calculations by 120 orders should evoke horror. After all, this means space-time fabric beneath us is stretched to limit. We're not monument fortress inhabitants, but tightrope walkers balancing over entropy abyss. But precisely in this fragility lies the most important lesson James Webb taught us. Science crisis isn't dead end. It is the only way to break through to truth. If data matched theory, we'd simply check box and stop developing. But mismatch, this noise in data, this Hubble tension, is crack in wall through which new physics light breaks. We stand at revolution threshold comparable to what Einstein and Planck accomplished in early 20th century. We again know nothing, and this is wonderful state. Look at this image. Now that solar system disappeared from view, only universe large-scale structure remains. Matter web permeated with voids. We are universe's way to know itself, and perhaps the fact that we exist despite incredible vacuum decay probability or constant drift speaks that our observer role isn't accidental. We record reality by very fact of our presence, turning quantum uncertainty into history. James Webb Telescope will work in orbit at least another 10 years. Every day, it sends Earth dozens of gigabytes of data, breaking old dogmas. Ahead wait discoveries, for which we don't even have names yet. We'll seek other civilization traces in exoplanet spectra, test multiverse theory, and try understanding what dark energy really is. This journey only begins, and it requires courage to look into darkness without averting eyes. If you, like me, feel this intellectual hunger, this awe before unknown scale, stay with us. Your support and interest allow us continuing to ask uncomfortable questions and seek answers where classical science comfort zone ends. Subscribe to these searches, share them, because universe understanding is our common collective task, impossible to solve alone. Now, looking into this absolute blackness on screen, I no longer feel fear before creation error. I feel gratitude that physics allowed us to arise, that light overcame billions of years to reach our telescope mirrors, and that we have minds capable of realizing our own insignificance before eternity. We sought time's beginning and found infinite possibility horizon. Universe isn't obligated to make sense to us. It is cold, indifferent, and perhaps mortal. But while we can ask questions, while we can wonder at impossible galaxies shining in darkness, we fill this emptiness with meaning. We are the meaning. And while our instruments catch photons from past, future remains open.